Welcome to Crestron Audio Certified Technician. In this video, we will go over what sound is by describing its physical properties. We will cover how audio interacts with different substances in its environment, the basic part of any audio system, and converting physical sound into signals for amplification, or for a reproduction system. This video will also cover sound as an electrical signal and how sound can be measured. To begin, let us discuss audio itself. Note that audio is often called sound in this industry. To start with, we will work from the fact that sound waves move through a medium that is then interpreted by the human ear. Sound is important to human beings, but there is an age-old argument that if a tree falls in the forest and no one is there to hear it, it does not indeed make a sound. The answer is clearly yes, but you need the ability for something to perceive the sound so that you can say, yes, it does of course produce a sound. Thus, sound waves move through things. Understanding the characteristics of what we hear are determined by what they are moving through. Sound when played underwater sounds distinctly different than sound played through air. Listening to music from the apartment down the hall will sound very different from if you listen to it in the same room. Because the medium of drywall will affect the sound characteristics differently than just listening through the air in the same room. That is because different mediums can absorb or reflect different sound waves. Air is a particularly thin material, which means that sound travels through it well. The speed of sound in air as an acoustic signal is 1,130 feet per second, or about 1,100 feet per second. In this video, our goal is to give you the understanding of sound and its behavior through a medium. Audio waves have two characteristics that affect the sound they make. Wavelength is described as the distance between successive crests of a wave. The other one is frequency, which is often designated by the standard term hertz. Frequency is described by hertz as the same number of waves that pass a given point per second. For instance, if we wanted to go from a first-order sound to a second-order sound, you must increase the number of waves in a given space. A second higher frequency sound has a smaller wavelength than a lower frequency sound. 1 hertz is equal to 1 wave per second. Sound spans 3 full decades of frequency. The first human audible decade is 20 Hz to 200 Hz. The second is 200 Hz to 2000 Hz. The third and highest audible decade is 2000 Hz to 20,000 Hz, or 20 kHz. This means that a 20 Hz signal, which is the lowest tone we can hear, has a wavelength 1,000 times longer than 20 kHz, the highest tone humans can hear. Because of this, it should be no surprise that low-frequency sound behaves much more differently than high-frequency sound, whether it is being radiated by a loudspeaker, picked up by a microphone, or reflecting around a room. One must always consider the effective wavelength of a sound when attempting to determine its behavior. A 20 Hz sound has a physical length of 56.5 feet, or 17.2 meters, while a 20 kHz sound wave has a frequency of 0.0565 feet, or 0.0172 meters. Because the 20 Hz wave is 1,000 times longer than the 20 kHz wave, it carries significantly more power or energy. That power means it can traverse far denser mediums effectively without dissipating, depending on the density and porousness of the material. Sound waves will either be absorbed or reflected by a surface. At times, refraction occurs, but that will be discussed in the section about sound shaping. Different materials are rated by their absorption coefficient. Each coefficient differs based on frequency. A coefficient of 1 means the material completely absorbs all sound. A coefficient of 0 means that the surface is completely reflective. According to this chart, glass has a coefficient of 0.03 for an 125 Hz wave, and 0.03 for a 1 kHz wave, which means that most sound waves in the hearable spectrum reflect off glass. By contrast, 4-inch fiberglass has a coefficient of 0.38 for a 125 Hz wave and 0.98 for a 1 kHz wave, which means that while a low end is still reflected at about a 2/3 ratio, it almost completely absorbs a 1 kHz wave. Most intelligible speech lives between 400 Hz and 4 kHz, so fiberglass would be a good soundproofing material for most things. Another medium that sound can travel through is copper. This is critical for sound reproduction. The typical audio system has three main components. First is the input components, or often called just simply inputs. Inputs are where the sound is represented as kinetic energy from sound waves and turns into electrical signals. The second component then is to take the electrical input and process it. This is often called the mixer. A mixer is used to address a listener's audio experience by matching closely all of the input signals. The mixer can also do audio processing for sound shaping to produce a final result that is pleasing to the listener. Finally, there are output components. Outputs convert electrical voltage back to kinetic energy for the listener's ears to interpret as intelligible sound. In order to transfer physical sound waves to electrical pulses that can travel a wire, we use a microphone. Microphones take the vibration of sound waves and convert them into electrical voltage. The key unit of measurement for electrical input signal is voltage pressure, which is most commonly referred to as dBu. dBu is the designation abbreviation for decibel voltage pressure. The father of audio transference across electrical cable is Alexander Graham Bell. He created the measurement and designated it as the bell. 1 bell made sense with telephones, but today we typically use only 1/10. 1 decibel is 1/10 of a bell, which is abbreviated with the letters lowercase d and uppercase b. This 1 bell is used to reference the level loss of an electrical signal across 1 mile of telephone wire. For most audio-video product, we describe the decibel using dBu. The suffix u added to the decibel denotes input or output level for audio equipment. For example, a dBu is a voltage pressure reference directly linked to the resistance encountered from a copper cable. 0 dBu specification is represented as 0.7746 volts RMS, or root mean square, which loosely means the average consistent load at the input. Audio input sources such as microphones, Blu-ray players, and preamps have their output ratings labeled in dBu. Most standard professional microphones standardize at -20 dBu output, which is commonly referred to as mic level, while other devices standardize at +4 dBu, which is commonly referred to as line level. Once we have converted the kinetic energy to dBu, it'll go into a mixer as an input source to allow us to shape it for the room or space we intend to use the sound. We will have more of this shaping in the next video. Thank you for watching.